First of all, we'd like to review the electric potential energies. We consider two charges, Q and Q sub 0. And between these two charges, electric force is acting between these two charges. This force is F equal 1 over 4 pi epsilon naught. If the distance between the two charge is r, this becomes Q sub 0 over r squared. This is the magnitude of the electric force acting between the two charges. Then we would like to move this charge into the new positions. So we consider this charge of the Q is placed at the origin, and we could move this charge of the Q sub 0 into the far away from the charge of the Q or approach the charge of the Q's. But when you want to change the position of the Q sub 0, you have to apply the force. Exactly same magnitude of the force, but opposite directions of the force. So this is F equal opposite direction. You have to multiply the negative sign. Minus 4 pi epsilon naught Q sub 0 over r squared. So you need to apply these forces to move this Q sub 0 to the new positions. Now we'd like to consider this charge originally exists in the infinities from the Q, and moving, and then keep moving. Finally, it becomes A. Then, how much energy is obtained by applying the external force of the F, this F. Actually, electric potential energy is increasing by this external force. So we'd like to find, so U A minus U infinity. This is the difference of the potential energies. Of electric potential energy. UA minus U infinity equal, you can use the integrals, U minus 1 over 4 pi epsilon naught Q sub 0 over r squared dr. You have to change the positions from the infinities to the A. And usually we choose, this is the conventions, to choose the potential energy at r equal infinity, this equals 0. This is the conventions. Then from these equations, we could find UA. You can perform these integrals. Minus 4 pi epsilon naught Q sub 0. Integrals of the 1 over r squared becomes minus 1 over r. Infinity to the A. So if you substitute in A is a plus minus sign, and the minus sign becomes positive. This is 1 over 4 pi epsilon naught Q sub 0 over A. So we have a potential energies. Electric potential energy. This is electric potential energy. Now we'd like to introduce a new term of the electric potentials. Electric potential is sometimes we could use a V or sometimes same notation of the use. Electric potential is defined U divided by the Q sub 0. So in the last case, we consider some test charge. This is test charge. This is the electric potential energy. This is the meaning the electric potential energy per unit charge. So we need to take into account the per unit charge. You have to divide it by Q sub 0. So potential energy. Sometimes we use a V. A it becomes 1 over 4 pi epsilon naught. Q over A. Or instead of A, you can use R. It's 1 over 4 pi epsilon naught. Q over R. So this is really convenient expressions. Now we'd like to go back to the questions. We consider charge of the Q is distributed around the conducting ring. So this is the conducting ring. Radius of A. Then find the electric potential at the point of P. So this is electric potential. This is the origin. So this comes X. Find the electric potential at the point P on the ring axis at a distance x from its centers. This is the question. Then we'd like to find out the distance between. We are going to separate into the number of segments of the ring. Each segment has the same amount of charge. Then we'd like to pick up the one of the segment. Then consider the distance between this segment of the ring to the point we considered. Then we apply the Pythagoras theorem to these triangles. Then this distance of R is correspond to the square root A square plus X squared. Then you can use this equation to find the potential. Every ring segment has the same distance to this point. We consider P, same distance. Then actually the charge of the Q is distributed on the rings. Then we can directly get the answer of this potential. VR is 1 over 4 pi epsilon naught. Q is charge over square root A square plus X squared. Okay, so this is the answer to this practice.